In this next video, I'm going to talk about eigenvalues and unitary operators. Unitary operators. Okay. So the textbook mentions two theorems. So first was theorem 11, which basically says that if you have a unitary operator, the eigenvalues of that unitary operator are going to be complex numbers with a unit modulus. So eigenvalues of unitary operators are complex with unit modulus. Okay. The second theorem, one labeled theorem 12 in the textbook, basically says that the eigenvectors of a unitary operator are mutually orthogonal. And so that first theorem has to do with the eigenvalues. The second theorem has to do with the eigenvectors of a unitary operator. Like I said, are mutually orthogonal. Okay, so these two theorems are going to be useful for us in quantum mechanics. One, because we like unitary operators, and the fact that we want to deal with normalized states, so we want to normalize to a good number, and normalizing to 1 sounds like a good method to do. And we're also looking for orthogonal states. We want to pick a basis. We want to pick a set of vectors that are orthogonal to each other, which will make life a whole lot easier when we're trying to disentangle the physics of what's going on. So let's just kind of go through and now kind of prove it the best that we can. So let's say you have a unitary operator, U, and it's going to act on a certain vector, which we're going to label as U sub I. So we're going with this new notation now, where we label the eigenvector with the actual symbol that's going to turn out to be the eigenvalue. So if we operate U on U sub I, what I should get is the eigenvalue U sub I and the eigenvector back again. So I could try this on a second basis. So the operator U acting on the eigenvector U sub j. So now I've got two bases, the i's and the j's. And that gives me an eigenvalue of little u sub j times the eigenvector back again. Okay, so let's do the inner product of these two. So let's take the product of u sub j with its operator acting on it, and since it's a bra, we have to operate with the adjoint, and we take that product with the eigen vector u sub I. Okay, right here. Okay, so if we operate with both these, we operate on the bra, we would get u sub j, a complex number. And if we operate with u, this operator, on the ket, then we would just get u sub I. And then we would get the inner product of u sub j back again times u sub I. Like so. Okay. But if we notice that remember, I should say, that the adjoint of the unitary operator times the operator is the identity. That's one of the definitions of these unitary operators. So now I can basically set on both sides that I have U, the inner product of the J state and the I state. So that's what's on the, that's this right here, is equal to these coefficients, U sub J star times U sub I times that same inner product again, U sub J and U sub I, right here. Okay, so now what we can do is subtract the right-hand side and move it over to the left-hand side. So I've got U sub J inner product with U sub I minus this stuff on the right-hand side is equal to 0. If I now factor out that inner product, I get 1 minus U sub J star U sub I times the inner product is equal to 0. And so now this can only be true if either the parentheses is equal to 0 or the inner product is equal to 0. Okay. So if I first look at the inner product, or I should say if I say I is equal to J, so I'm in the same basis, then this inner product, U sub I with itself, is not going to be equal to 0. Because this inner product should be should be positive semi-definite. And so that in that case, that means the parentheses is equal to 0. Like so, which means, and actually I should go back and change this because I is equal to J. So what it means is that 1 minus the complex conjugate U of I times U of I is equal to 0, which means that U I complex conjugate times UI is equal to 1. Okay. So that proves to us that these eigenvalues are complex numbers. So we're taking the complex conjugate of these numbers, so UI and its complex conjugate UI. So they are complex. We have to take the complex conjugate to multiply them together, and the product of those gives us a modulus of 1. So it has a unit modulus. Okay. So the second theorem about the eigenvectors, now let's consider the case of I not equal to J. So now what we're left with is an inner product of U sub J times U sub I is equal to 0. Okay. And what that tells us is when we have these two vectors in two different bases, a basis I and a basis J, if the bases are not equal to each other, I is not equal to J, then those two vectors are orthogonal. So this leads to the conclusion that our eigenvectors are going to be orthogonal to each other. So is basically orthogonal perpendicular to U sub I.